Alright, so this is my video on basic 1D heat conduction and Fourier's law. First, let's talk about the three primary methods of heat transfer, which include conduction, convection, and radiation, and we'll be focusing on conduction. So conduction is defined as the transfer of energy between adjacent molecules, and it is slower than bulk flow or convection, which we will touch on in a later video. There are two submechanisms of conduction, the first being molecular interactions, which is the result of motion of particles connected through bonds, and there is also free electrons. And free electrons are characteristics of pure metallic solids, and they essentially are loosely bound electrons that transfer energy very well. Let's get on to actually defining Fourier's law through a little example. Let's say we have a house, and the inside of the house is warm, and the outside of the house is cold. So let's zoom in on that sort of wall where we have the inside of the house being hot and the outside of the house being cold, and the wall's thickness is defined as L, the outside is, say, temperature 2, and the inside is temperature 1, and the wall over here has an area of A. So let's lay out all those variables right here. And with these, we can define what heat transfer is, which is represented by a Q, and it has the units of joules per second, also known as a watt. So observationally, we can determine how Q is related to these different variables up here. For instance, if the house cools faster, that means we know that Q is increased, and if the house cools slower, that means we know Q is decreased. So if we increase the wall's thickness, we can see that the house cools slower. Therefore, we know that Q is inversely proportional to thickness. And if we increase the wall surface area, we can cause the house to cool faster, which means that Q is proportional to area. And if the outside gets colder and the inside gets warmer, that means the house cools faster, which means that Q is directly proportional to delta T, the difference in temperatures between the outside and inside. So with this, we can sort of write a balance. A is on top, L down here, and then delta T, but we're missing something, and that is thermal conductivity, K, which is determined empirically, that is through experiment, and is a property of the material itself. It has the units of watts per meter Kelvin, and it is temperature dependent, technically. That means it does change with temperature, but oftentimes this is ignored for the sake of convenience or because it makes things simple, and we'll just stick that K in here. Now this delta T over L can also be represented as dt over dx. And the reason this minus is in here is because it defines the directionality of heat transfer, which is that heat moves from hot to cold. That's why the negative sign is in here. Uh, when it comes to defining materials, we have isotropic materials, which are internally consistent without a preferred direction or path for heat transfer. So that is K is equal in all directions. This is usually your metals and glasses. And conversely, we have anisotropic materials, which do have inconsistent internal directions when it comes to heat transfer. K is different in different directions, and wood is the go-to example for an anisotropic material. This is heat flux, and heat flux is essentially just Q divided by A, which gets you this sort of equation right here. And now we can move on to the conservation of energy for a temperature profile, Tx. And this is very important, mostly because conservation of energy is a topic that expands outside of heat and energy balances. It's just very important. Now, let's define conservation of energy very broadly. We have a rate of energy accumulating is equal to the rate of energy in minus the rate of energy out, which is added to the rate of energy generation. Now, one might argue that energy cannot be made or destroyed, which is true, but this is moreover other forms of energy being converted into thermal energy. Think of like burning wood as turning one form of energy into thermal energy. But oftentimes, this can get very, very complicated very, very quickly, so we make some simplifications. One of these simplifications is making it unidirectional. It only moves in one direction. We'll say it's the x direction, so we don't have to worry about 3D or this pesky del function. We only have to worry about the one direction. And we can also make it so the system is steady state. That is, there is no accumulation within the system. Any change in variable with respect to time is 0. The system is the exact same 1 minute from now as it will be 1 million minutes from now. There is no heat generation. The material is not a wire, it does not produce heat, there is no internal sort of reaction going on where bonds are being broken or to make energy. That isn't happening here. So with all this, let's do a derivation to get a temperature profile. So accumulation goes to nothing, generation goes to nothing, and here we can say that the heat of energy coming in is Q at X, and the rate of energy coming out is at Q plus dx. So here, this is at point 0, this is at point L, and this is sort of a boundary condition. At x equals 0, it's t1, and at x plus dx, or L, it is t2. This will come in handy later. So with this, we can say 0 is equal to q at x minus q at x plus dx over delta x. And we divide it by delta x mostly because it's 0 on this side, so there is really no effect. But also, this is the definition of a derivative. And subsequently, we can say dq equals dq over dx is equal to all of this. So using Fourier's law, we can determine it thusly, which still equals 0. And we can now rearrange this equation. So let's get a d on this side, dt dx equals 0, dx integrate, this falls out, so you're just left with dt over dx, which is equal to just a constant when you integrate 0. So it's just a constant. So let's do another rearrangement so that c1 is on this side, dx is on this side, and we integrate once more to get p of x equals to c1x plus a second constant now. So here is where those boundary conditions came in handy. Let's say we know that t at position 0 is t1, which equals c1 times 0. This falls out, plus c2. So therefore, c2 is equal to t1. Now we know that tx is equal to c1x plus t1. Now let's define this x at position L, where we know it to be equal to temperature 2. So C1 times L plus T1. Let's isolate for C1. C1 equals T2 minus T1 divided by L. Now let's plug all this in to get our temperature profile. T2 minus T1 divided by L times x plus T1, and this would be your temperature profile. Let's put this into action. We have a 1 by 1 by 1 meter cube, which has the temperature of 120 degrees Celsius and is covered in 2 centimeter thick insulation that has a thermal conductivity of 0.04 watts per meter Kelvin. The outside temperature is 40 degrees C. What is the heat transfer rate? Q equals what? So let's just draw out that equation. K A on top divided by L, and let's just say that's the change in temperature. So what do we know? We know the two temperatures, we know what K is, we know what L is, but area is not explicitly given, but we can easily find it. So one face of the cube is 1 meter multiplied by 1 meter, which equals 1 meter cubed, which is the area of one face, but since it's a cube, it has 6 faces, so we have 6 meters cubed. So now let's fill in the blanks here. We know that minus 0.04 watts per meter Kelvin, area 6 meters cubed, and the change temperature all over L, which is 2 centimeters, which is the thickness of the insulation. Right off the bat, you can sort of notice that there is a unit mismatch. These are centimeters, these are meters. So let's just quickly do a unit conversion, there are 100 centimeters in 1 meter, so centimeters cancels out here. The meters here also cancel out, and now we're left with this Kelvin term and this Celsius term, and you might think that you have to convert Celsius into Kelvin. That's not necessarily what you can do that, but you don't have to do that because a difference in temperature in Celsius is the exact same as that difference in temperature in Kelvin. So we can leave it just like so and say that we convert it to Kelvin to cancel out this term here and cancel out the units here. And now we can simply plug in, and this gives us a value of 960 watts. All right. Thank you for watching, and I hope you learned something.